Hello, welcome to this lecture on biomathematics. Today, we will try and think and discuss how do we apply many of the mathematical techniques that we learned to understand a bit of thermodynamics. And because so basically we have to learn or discuss a bit of thermodynamics, because thermodynamics is a very essential feature of essential tool to understand various biological systems. So, today's title is basically statistical thermodynamics of biological system, and the question is why statistical thermodynamics? Why should we learn this? Why first of all, when I say statistical thermodynamics, you can see there is this term called statistical. So, something that we learned so far, including biology, probabilities, averages, standard deviations, all these things we learn in statistics and probabilities. So, this will all be applied here, and we will be using all these tools to understand statistical thermodynamics and in turn various biological systems. So, basically thermodynamics involves some amount of mathematics and some amount of physics. So, we have to discuss a bit of physics also while we are discussing various biological systems. But the focus will be how do we apply the techniques that we learned to understand all this biological system. So, now when we say thermodynamics, first of all, let us quickly discuss why do we need thermodynamics, and in particular statistical thermodynamics, because basically all the biological systems, they are at such a given temperature, mostly in our case is 37 degrees Celsius. So, any protein or any biomolecules that you think of, they are at 37 degrees Celsius and they are in a medium, typically like mostly water. So, one has to, whenever we have to understand or think about biomolecules or biological systems, we have to think of that some objects or some molecules or a system at 37 degrees Celsius in some medium like water. So, let's think of some molecule. So, for simplicity, let's even think of, so there is water, and there is a bunch of particles. So, atoms like these are connected. So, you could think of the simplest model of any protein could be like two balls connected by some springs. So, think of some molecule like this, like two atoms interacting via a spring like potential. So, the two atoms, they are interacting like a spring. What does it mean? What does this mean is that these two atoms would like to be at a certain distance, and there you don't, when they are taken apart, they will be attracted, and when they are taken too close, they will repel. So, the spring has this property that if you take them too close, you will have a resistive force. So, this will resist coming together. It will also resist going away, because spring pulling is also need force and the spring pushing is also needs force. So, this is a good example of simplest case of biomolecule would be something like this, two atoms connected by a spring. Okay, now this is a model, this is something that we mimic to mimic a biological system. This is the simplest model we can think of. Now, imagine there is water. So, there is water, and these dots are what? These dots represent water, and all these water molecules do Brownian motion. So, these water molecules do Brownian motion. Why do they do Brownian motion? Because they are all at some particular temperature T, which is typically like 300 Kelvin or around, so like something around 300 Kelvin. So, at this temperature, all this water molecules do zigzag motion. When they do zigzag motion, they go and hit these atoms from all sides. So, this arrows represents water molecules going and hitting these atoms. So, when water molecules go and hit these atoms, they will also start vibrating. So, essentially what happens is that these molecules will have to vibrate, they will have to fluctuate, their position of these atoms will fluctuate. Now, think of certain cases. For example, let us think of there is some two charges in water. So, think of two charges in water, plus charge and minus charge. They are at certain distance r apart, and from physics you know that the energy will be like q by 4 pi epsilon 0 epsilon r. The energy will have 1 over r relationship. So, this is basically we don't have to worry about all these constants, it is some constant, do not worry about any of this. This is some constant divided by r. So, this will be some constant, let me call this A divided by r. So, this is the typical energy of Coulomb energy, right. So, okay. So, now there is water and water will do Brownian motion at a temperature T. So, when they do Brownian motion, there is an energy which we can call thermal energy. So, there is this thing called thermal energy. So, what is thermal energy? Thermal energy is the energy due to the thermal motion. So, the thermal energy is kBT. Now, where kB is Boltzmann constant and T is temperature. So, this is the rough amount of thermal energy will be 1 kBT. Now, Coulomb energy is some constant divided by R and thermal energy is kBT. So, it turns out that for a particular some value of R, when R is equal to A by kBT, when R is equal to A by kBT, these two thermal energy and Coulomb energy will be equal. So, when R is equal to A, you can see that if you substitute R is equal to A by kBT, this two will be equal. So, this is basically Coulomb energy. So, this is Coulomb energy and this is thermal energy. So, when R is equal to A by kBT, Coulomb energy is equal to thermal energy. So, now it turns out that this R, if the order of nanometer, this will be equal. If this is so, it turns out that when R is of the order of nanometer, these two will be equal. That is what when you typically substitute these numbers and see, you will find that when R is of the order of nanometer, these two will be comparable. Thermal energy, Coulomb energy and thermal energy will be approximately equal. So, what does this mean? In biology, all the length scales, nanometer is the typical length scale, like what is the one base pair of DNA is 0.34 nanometer. Like typically nanometer is the distance between atoms, more molecules, various distance between molecules in the molecular size, the size of the typical distance in biological biomolecules is basically of the order of nanometer. What does that mean is that at this length scale, the thermal energy is comparable to, for example, here the Coulomb energy. This is even true even if you take some other energy like elastic energy, the bending energy, if you take the bending energy, some lengths of the order of, if you take the DNA bending energy, when the length is about 50 nanometers, these energies are comparable, or 100 nanometers of the order of 50-100 nanometers, these two energies will be comparable. The thermal energy and the bending energy, the energy needed, elastic energy needed to bend DNA will be comparable to the thermal energy. If we can have a quick look at this. So, it turns out that the bending energy of the DNA can be written as 1 over r square into L into some constant kappa. This is the bending stiffness. So, this is the bending energy, and when will this be equal to kBt? So, this is the bending energy of DNA of length L. So, if this is the energy, if you have a DNA of length L, this is this if you take as 2r. So, then you have to bend it to a circle. So, let us say you have to bend it to a circle of, so let's draw this a little more carefully. So, let's draw a circle. So, if you want to bend it to a circle of radius r, this will be this, and we can ask the question, what will be when will this be bending energy will be equal to kBt, and I would not go into the detail of this because it is not, the important point is not this here, but I just want to say that even for the bending of the DNA, you will find out that when r is of the order of about 100 nanometer, you will find that the bending energy is comparable to kBt. So, that means, what does it mean is that even if a DNA will at that temperature which is about 300 Kelvin will start bending. So, DNA will not be straight anymore. If the DNA is of the length of 100 nanometer, they will start bending. So, what does this mean? This means that all the position of the molecules will start fluctuating. So, we saw that if we have in water, if we have molecules connected by spring, their position will start fluctuating because they get hit from all directions. If you have a filament like DNA in water, because of this thermal motion, because of these molecules coming and hitting this will start bending. So, all the biomolecules will start fluctuating. So, if you think of the biomolecule, they will just start wiggling in water. So, this thing is called thermal fluctuation. So, let me tell this word, thermal fluctuation. What does thermal fluctuation means? Is that the fluctuation in position of atoms of biomolecules due to Brownian heat, thermal motion, due to thermal energy. The fact that the water molecules and the molecules around do Brownian motion will lead to the fluctuation in position of various molecules, atoms in biomolecules. So, these biomolecules will start fluctuating. The DNA or the proteins will have their position, that they will bend and they will do wiggly motion. The atoms will start vibrating or moving around, or the charges will start moving around. So, they will be very dynamic, and the reason behind that is basically the thermal motion. So, given this fact that given that they are not static anymore, at temperature of 300 Kelvin, these atoms in biomolecules are not static anymore, they keep fluctuating all the time. So, if you want to talk about the distance between two ends of a DNA or the distance between two parts, you have to always talk in terms of statistical averages. What is the average distance between two atoms? What is the average? So, that is where you would need to use ideas from statistical thermodynamics. So, there is the need of statistical thermodynamics. So, to understand the configuration of biomolecules, for example, we need to use statistical thermodynamics. Now, let us go and think of some stuff that we already know, something you have heard in thermodynamics. You have heard terms like energy, entropy, enthalpy, free energy. So, let us quickly look at it, because there is very interesting mathematics behind all this, and I will briefly discuss. So, the statistical thermodynamics is a course in itself, but in a few lectures I want to give you a gist of how do we apply various mathematical techniques to understand these quantities in a better way. You might have studied various formula like H is equal to E plus PV, G is equal to H minus Ts, and so on and so forth. What is all this behind this formula? Like, can we understand this in a better way? And yes, we can, and we will have to use some ideas from mathematics, and then this will be much more clear. Okay, so let us think about this. So let us first discuss some of the terms that we already came across in biology, in thermodynamics. So that is what today we will do. We will discuss some of this. So we will start with this term energy, which you all know what is energy. So we said that we will first think of the system. We said that we can think of proteins as two balls connected by a spring. This is a way of thinking about protein. This will help us. So, two balls you can think of as two atoms, and they are connected, they are interacting by some kind of spring like interaction. Now, you know that the energy for this system has to be half k into r square. This is the spring energy. So, this is the energy for such a system. If you have, instead of this, if you have two charges, that is the distance r, we said that the energy is Coulomb energy, which goes as 1 over r. So, always in some other cases you might have had like van der Waals interaction, the interaction energy will have some particular form, a r power 12 minus b r power 6. You might have seen such a formula for energy. So, energy is all this, depending on the interaction you will have different energy, but all these energies, Coulomb energy, spring energy, van der Waals energy, in all these cases it is important to know that energy is a function of the distance r. So, this is what typically happens, E is a function of r. So, now you can even think of bending energy, and this also will turn out to be a function of r. We will discuss this a little more in detail later, but for the moment let us think of the energy that we know. So, whenever we say energy, we would mean the interaction energy, the Coulomb energy or spring energy or Lennard-Jones energy, or that is called the van der Waals interaction energy. So, energy will be typically the function of the distance or the positions of the atoms, because the interaction will depend on the distance. So, therefore, E is a function of r. So, when I say energy, this is what examples are this. Now, another term that we all have seen and which is not very clear to many of you might be this term called entropy. So, what is entropy? So, we will take a bit of time and then discuss this in detail, and the mathematics associated with this entropy, and how do we calculate entropy. So, we know how to calculate energy. Energy, we know the formula k r square, half k, if you know k and if you know r, k r square can be calculated. Q by q and q2 by 4 pi epsilon 0 r, this can be calculated. So, the energy can be calculated once we know the formula. But how do we calculate entropy, and what is entropy? So, it said that entropy is basically a measure of disorder. This is something that we all learned. Entropy is a measure of disorder. And how do we quantify disorder? When we started this lecture of mathematics for biologists, we said that our aim is to quantitatively say, okay, this is what it is. So, when we say disorder, amount of disorder, we need some measurement, some quantity to really quantify and say, okay, for this case, the disorder is this much. Mathematics, we would like to say everything in numbers. So, we would like to say disorder is 3.157, disorder is 23 point something. So, we know that if disorder is 23 and disorder is 10, one system has disorder 10 and one system has disorder 23, we know that one has more disorder than the other. So, we would like, if possible, to represent disorder as a number, so that we can compare. So, how do we tell entropy as a number? Can we do that? So, that is what we will discuss first. How do we do that? So, let us think of a bit about disorder first. Now, so for this, let us think of some example. Let us think of books in library. So, if you go to a library and if you look a particular stack, there will be a set of books. So, let us say you have a stack and this stack has like 5 books, 1, 2, book 1, book 2, book 3, book 4 and book 5. And these books in the library will be arranged in a particular order according to either their serial number or accession number. There will be some particular number given to each book, and in this particular, in a particular rack, this books will be arranged in a particular order. So, you go to library today and have a look at the stack of books, and you will see that this is arranged B1, B2, B3, B4, B5. You come back tomorrow and again they will be arranged in the same manner. So, you keep taking photo of these books every day, and each day you will see that they are arranged in that particular order. So, it is highly ordered arrangement, the books in library. Now, imagine that you take all these books, all these 5 books, and take to your home. Then you arrange these books in your shelf. So, in library, if somebody takes out this book to read, after reading they will be kept back in exactly in the same position. So, librarian will make sure that the books sit in that order, so that it is easy to access this book, easy to get these books. Now, at home we have only like very few books. We don't really care about keeping in a particular order. Like we don't know which is first book, second book. We don't really care about accession numbers or serial numbers at home. So, at home we take all these books and then we will put maybe in some particular order. We will put like B3, B5, B1, B2, B3. This is the way we will arrange in our home. Our home we will arrange in our rack, in the bookshelf. We will arrange the books in this particular fashion. Now, we take out some book B1 to read, and the next day when we keep it back, we keep the B1 at the end after B3. So, let us say we keep B1 you kept, B3, B2, then B5, sorry, there is B4 here actually, B3, B5, 1, 2, 3, 4, 5. Okay, so, we kept this B1 here, there is B4, then B2, then B1 is removed, then B5 and B3. So, 1, 2, 3, 4, 5 books. So, the order changed, it became B3, B5. So, there is no particular, now some another day we might take all the books to read, and when we keep it back, we need not remember this order. We will keep in some fashion you will keep maybe B5, B1, B4, B2, B3. We might keep in this order. So, there is no particular order for us to keep this. So, the arrangement at our home is less ordered compared to the arrangement in the library. So, now how do we quantify this? This is less ordered and more ordered. So, if you take this pack of 5 books and if you look at the position of the books, in the library each book will have only one position. First will be B1, like the particular arrangement in the library will be B1, B2, this will be the exact arrangement. So, there is only one particular way we can arrange this book. On the other hand, at our home, we have many ways of arranging this book. So, let's simplify this and make it only 3 books. So, that is easier to write down all the arrangements. So, in the library, the books will be arranged B1, B2, B3. This is what in library. But at our home, one day we might be arranging it in B1, B2, B3. Next day we might be arranging B1, then B3 and then B2. Another day it could be B2, B1, B3 or B2, B3, B1 or it could be B3, B1, B2 or B3, B2, B1. So, we can all these possible arrangements are possible. We can arrange the books in this way or in this way, in this way. So, this is at home. So, home shelf. So, first day we might arrange in this way, but we take out all these books and when we read and keep it back, one day it could be like this, another 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 day. So, there are 1, 2, 3, 4, 5, 6 possible arrangements here. Just check carefully, look at it. Did I forget any arrangement? I think I haven't. So, there are this many possible arrangements, I think. Yeah. So, this is all the day it will be one arrangement only. Here there are 6 possible arrangements we discussed. So, this we call ordered, this we call less ordered. So, library is more ordered, this is less ordered. So, entropy for this library is this way small. Entropy is a measure of disorder. So, this will be more entropy and this will be less entropy. So, this particular arrangements we can call as states. We can call this as states. So, it turns out that the way to define entropy, that entropy S, so this is the notation we will use for entropy. Entropy S is proportional to number of possible arrangements. In the library there is only one arrangement, but at home we had many possible arrangements, so there is more entropy. And it turns out that the correct definition of entropy in biological thermodynamics is basically, or in thermodynamics, is minus Kb log number of states. So, let me call this omega as the number of states. Omega is number of possible states or arrangements. So, we will discuss what do we mean by states. So, what in our case, when we in states, this is position of books. So, in biology, states means typically would mean position of atoms. If one protein molecule has like 3 atoms or 2 atoms, if it can get arranged, positioned in different positions, many arrangements are possible. So, let's quickly even discuss another example of order and disorder that we see. So, you might have seen like parking lots where cars are being parked. So, what is the one feature that you have seen in parking lots? So, many of the parking lots will have like lines drawn like this for cars to park. So, the first car, one car will park here, next car will park here, next car will park here. So, there are cars are very well organized here. If you did not have these lines, then one car could park here, another car could park here, another car will park here. This could be some such arrangement, or you will see that one car is parked here, one car is parked here, one is parked here, and some such arrangement. So, here this is very ordered arrangement, less entropy. Here is highly disordered, no ordering. So, this is more entropy. So, each of this car, here this car can have only one position because this is restricted by this blocks, this lines. You shouldn't park beyond this lines, only within this line you can park. So, there is only one position for this car inside this box. But here there is no particular restriction here. You can take any position you want. So, then people start parking anywhere you want. So, there are too many possibilities. So, entropy is proportional to the number of arrangements, number of states. So, this is one state, this is another state. You can think of all states, and the more the position for each car, more the states. So, there are large number of states you can think of. So, this is one state, this is another state. So, this is another example of disorder and order. So, more entropy for this case and less entropy here. So, now we have to think of this number of states. So, if you know the number of states, we can get entropy, and it is proportional. But how is it proportional? It turns out that, as we said, the formula is S is kb ln omega. It is logarithmic relation, and there is some particular reason, because if you have two systems, like log has a particular property that log of a b is log a plus log b. So, if you have a system like which has omega 1 state and some other system which has omega 2 states, and the total state will be like, so for this we can think of this as, like, let us say you are tossing a coin. When you toss a coin, it has two states, head or tail. So, omega 1. So, this is head or tail, this two states. Omega, you can think of some other system which is throwing a die. When you throw a die, here are 6 states. Like one, you might have played snake and ladder and play things like this. So, where you throw a die and it will have 6 faces, and each face is a state. So, there are 6 states possible for the die. So, this has 1, 2, 3, 4, 5, 6. So, there are 6 states possible for a die. So, now imagine that you have a die in one hand and a coin in another hand, and you are throwing each of at the same time, both of them at the same time. So, the coin will come head or tail, die will have 6 of this 1, 2, 4, 5 or 6. So, now you ask the question, what is the total number of states? When the coin is head, the die can have all the 6 states, 1, 2, head 1, head 2, head 3, head 4, head 5, head 6. When coin is head, die can have all 6 states. When coin is tail, the die can have 6 states. So, there will be 12 states. So, there will be like omega 1, the total number of states will be omega 1, omega 2, which is 2 into 6, there will be 12 states. Now, entropy, the total entropy of this system together will be sum of this entropies. So, this property that S is total system of, so S of coin and die C D, let me write, is minus K B log omega 1 omega 2. This is 2 into 6. So, this is minus K B log omega 1 plus minus K B log omega 2. So, this is basically entropy of the coin plus entropy of the die. Entropy of the dice that we, so throwing dice will have some particular entropy, and the sum of this will give you this. So, this particular property that the sum of these two will give you the combined entropy. To have this property is good to have long. Any function having log has this nice property that if you combine these two systems, the entropy of the combined system will be the sum of these entropies of this individual systems. So, that and such a property is being, entropy has such a property, and therefore, to have it, it is good, it is appropriate that we have this function as log. So, that is the reason why there is a log. So, now we know if we can count the number of states, we can understand that we can understand entropy. So, entropy is K B log omega in simple cases, but there is an assumption here. This is only true for such systems where all the states are equally probable. When you toss a coin, head and tail are equally probable. When you toss when you throw a dice, all the states 1, 2, 3, 4, 5, 6 are equally probable. If they are not equally probable, let us say head is more probable than tail, or if it is a biased coin, or if it is dice which has some bias, like if there is probability of 1 different from probability of 2, P3, the probability to have all this is different. If they are different, then the entropy is given by this formula sum over I Pi log Pi, where Pi is the probability to have state I. So, if it is for the case of coin, S will be if minus K B sum over I. So, sum over the sum here would mean probability of head log this is one state plus probability of tail log probability of tail. So, this is the example for, if this pH and PT are equal, you put pH is equal to PT equal to half. So, you take this case, this formula, and here you put pH is equal to PT is equal to half. What do you get? Half log half plus half log half. So, you will get S is equal to minus KB, half log half plus half log half will be 1 log half. This is log half is log 1 minus log 2. This will be minus KB, sorry, this will be plus KB log 2. So, this is, if the probabilities are equal, you will get the old formula that log of number of states times KB. There are two states, head or tail, and KB log 2 will be the answer. So, when probabilities are equal, this formula will be equivalent to the formula of KB log omega. Otherwise, the general formula for entropy is basically this. This is attributed to a famous scientist called Shannon. However, this is the formula when the probabilities are different for each state. Okay. So, we understand, we know how to calculate entropy. So, if you know the probability of a state and then if you know how many states are there, we can calculate the entropy, and by state we mean position. So, let us quickly do some quick calculation of entropy of in some cases. So, let us think of the simplest example, that is, let us think of a protein, and a very simple case for a protein, which is basically 3 atoms connected by some bonds. So, let us think of this is one atom, another atom, and they are connected by some bonds. What is the entropy of this system? So, we know that depending on the interaction, we can always calculate energy. Now, we can ask the question, what is the entropy of this system? So, now these 3 atoms can have any position we want. So, let us imagine that this can have any position that we want. What does this mean? This means that this can have this particular configuration. Now, let us say this atom moves here, then it can take some positions like this. It can take some other position. So, this 2 atoms like this, and the third atom moved here. You can think of some position like this. Like this. So, you can think of many positions. In all these cases, what changes is, in this simple case, this angle between these 2 lines, they change. So, if you think of this angle, so let us say if you call this angle as theta, in this case each of this angle between, so this angle can take any value starting from 0 to 2 pi. So, the total number of states will be all possible sum of this conformations. So, you can take theta any value from 0 to 2 pi. So, if we take this into account, we can get the entropy of this. So, let us do this. So, entropy will be, we can write entropy as integral 0 to 2 pi d theta. This theta can go from any value from 0 to 2 pi. So, this will turn out to be, the answer will turn out to be of course 2 pi. So, the entropy will turn out to be 2 pi. Now, if you think of two such molecules, so let us think of now there are 2 angles we can think of. This angle can be anything and this angle also can be anything. So, there is theta 1, theta 2, and theta 1 can be any value, theta 2 can be any value. So, the entropy as in this case will be integral 0 to 2 pi d theta 1, 0 to 2 pi d theta 2. So, basically the answer will be 2 pi into 2 pi. So, 4 pi square. So, we can generalize this to n such angles. So, we can draw more lines. So, we can now think of one protein molecule which has n such bonds. So, this is connected by n plus 1 atoms, n plus 1 atoms connected by bonds. Each of this angle, let us say theta 1, theta 2, theta 3, theta so on and so forth. So, there will be like n angles, theta 1 up to theta n, there will be n such angles, and the entropy will be given by d theta 1, 0 to 2 pi. Each of this angle can take any value. So, the total number of conformations will be this integral 0 to 2 pi d theta 2, 0 to 2 pi d theta 3, up to 0 to 2 pi d theta n. and the answer will be 2 pi whole power n. So, the entropy will be 2 pi whole power n. So, this is the way we can calculate entropy. Now, think of something in protein biophysics that that this theta cannot actually take any value you want. So, in most of the cases you might have heard of something called a Ramachandran plot. So, most of the proteins, the angle between amino acids, there are some restrictions. They are known as Ramachandran, Professor Ramachandran, who was one of the eminent scientists from India, he discovered that certain atoms, certain planes have to be in a particular restricted manner. So, there are particular angles which people call dihedral angles, or more like phi and psi. You might have studied phi and psi in biophysics. So, if you know that phi and psi, the values of these angles are restricted, all the states are not equally probable, then the entropy is not all possible states, but basically if you know, then the states with those angles are more probable, then the entropy will be slightly different. So, then you have to use the formula pi log pi. So, we will discuss that, but if all states were equally probable, if there is no restriction, then we know how to calculate entropy. Now, we will come back to the other case of when there is a restriction, how do we calculate entropy, we will come to that. So, once we know energy, once we know entropy, there is a important quantity in thermodynamics, and that is known as free energy. So, this is the next quantity, which is basically the quantity known as free energy. So, free energy is typically, the definition of free energy is sometimes written as F, sometimes written as G. So, we will today discuss F and we will come to G, and we will see the difference between these two in the next class. But Gf is basically energy minus temperature times entropy. F is E minus Ts. So, if we know how to calculate entropy, we know how to calculate energy, which is either half kr square or q1 q2 by r, or this is some value. With this we know how to calculate, and we know how to calculate T. So, we know how to calculate free energy. So, if you calculate free energy, why is it useful? So, it turns out that in thermodynamics, if you have a system, that system will reach equilibrium when the free energy of the system is minimum. So, when you plot free energy, typically at some occasions we have seen free energy as a function of some variable, there will be some minima like this. So, this point where the free energy is minimum, so with some variable, let us say r. So, then there is a particular state where this free energy is minimum. So, this state will be the equilibrium state. So, equilibrium so in thermodynamics, equilibrium is a state. When I say state, it is the conformation of a protein, or a configuration, or a position of atoms in a position of molecules in a protein. So, the molecules will take this particular position, those particular position, such that the energy, the free energy F is E minus Ts is minimum. So, that will be the most preferred configuration. So, when I say equilibrium, that will be the preferred conformation. So, we will discuss about this free energy, equilibrium, etc. in the coming classes, and we will go and understand the statistical concept here in little more detail. but one thing we saw is that there are many conformations possible because of the thermal energy and the heat due to the Brownian motion of water particles, for example, or the particles in the medium. Each protein or each biomolecules can have large number of states or large number of conformations, and therefore, one has to talk about statistical quantities, and we will be using ideas from statistics here, and we will see, we will discuss a little more in detail how do we calculate free energy and how do we use it to predict some things. So, today we learned about energy and entropy and briefly discussed about free energy. So, three things: energy, entropy and free energy. We will discuss about the free energy in detail a little more tomorrow, but the idea basically I want to convey today is that one has to use ideas from statistics and mathematics to understand thermodynamics, and which in turn will tell us about biomolecules and the biology, various biological systems. So, many things we discussed so far actually without discussing involve some amount of thermodynamics, like Nernst equation or Einstein's equations, but today we will discuss some other quantity in the coming lectures. Few lectures we will discuss few other quantities formally, and we will see how do we use mathematics for that. So, with this I will stop today's lecture and see you in the next lecture. Bye.